Students, let me welcome you all to a new edition of physics. In this edition, I'll resume talking about wave-particle duality. We'll explain photoelectricity. As a matter of fact, photoelectric effect, cannot be explained by theories of classical physics. But Einstein managed to explain it. How he managed to explain it, to know it, let's get started. Wave-particle duality. Wave-particle duality. Photoelectric effect. What about photoelectric effect? We want to, to know it, to define it. What is this effect? Photoelectric effect is the emission of electrons from some metals when irradiated with electromagnetic radiation of sufficiently high frequency. I'll say it again. It is emission of electrons from some metals when irradiated with electromagnetic radiations of sufficiently high frequency. And pay attention to these words, sufficiently high frequency. Okay? Einstein, as a matter of fact, tackled the photoelectric effect. In 1905, he saw that all experimental laws could be explained. It was assumed, that atoms can only absorb light energy in discrete energy, packets. So the phenomenon, the effect can be explained if we assume that atoms can only absorb light energy in discrete energy packets. We call it quanta or photons. Okay? It is exactly as Max Planck said. The atoms can only absorb light energy in discrete energy packets or quanta. Okay. Light quanta are called photons. Photons are indivisible. So each photon gives all its energy to one electron. So, let me say it again. Light quanta are called photons. And photons are indivisible. So each photon gives all of its energy to just one electron. Okay. Einstein showed that this is the most important thing, that the energy per photon, the energy possessed by just one photon, by a single photon. Okay, he showed that energy per photon of the electromagnetic radiation should be at least equal to the work function. Should be equal to a certain value. We call it work function. So as to manage to extract an electron from the surface of the metal. Let me say it again. Einstein showed that energy per photon of the electromagnetic radiation should be at least equal to the work function. We'll define work function. Okay, of the metal to eject electrons from it. And when a larger photon, when a photon having energy larger than the work function, is supplied, what happens? It is absorbed, and the surplus energy is carried by the electrons as kinetic or kinetic energy. Okay, so we need to repeat it again. Einstein explained the effect as follows. Once again, if the photon energy is h nu is equal to the work function So work function is denoted by EW, and it is equal to H nu C. Nu C, new critical frequency. If the photon energy is equal to the work function, what happens? This is the first probability. Photon energy H nu is equal to the work function H nu C. What happens? The photon energy is just sufficient to eject an electron, and the electron is released from the metal, but without having any kinetic energy. Okay, the photon energy is just sufficient to eject an electron, and the kinetic energy of the freed electron is then 0. This is one possibility. Okay, note your attention, please. Please note, we'll define work function. Work function depends only on kind of metal. What about work function? It is the minimum quantity of energy. It is the minimum quantity of energy required to extract an electron from a given metal surface by a photon. It is the minimum quantity of energy required to emit an electron from a given metal surface by a photon. Second probability, if the photon energy H nu is greater than the work function, what happens then? The electron is freed, is extracted. Okay, the electron is freed, and the energy difference, okay, the difference between the energy of the photon H nu and the work function appears on the electron as kinetic energy. Okay, so the difference between H nu and work function, yes, take the form of a kinetic energy half mv squared. And H nu minus EW equals half mv squared. We can say H nu minus EW work function equals H nu C is equal to half mv squared. Okay, so H is Planck's constant is taken as a common factor. Nu minus nu C equals half mv squared. Okay, this happens when the energy of the incident photon is larger or greater than the work function. The difference, the surplus, appears as kinetic energy. What if it is equal to the work function? Okay, the electron is freed but having no kinetic energy. Okay, so we can say H nu minus H nu C is equal to half mv squared, where v is the maximum velocity of the photoelectron, the electron emitted by photons. We call it photoelectron. M is its mass. Okay. Nu is the frequency of the radiation, frequency of each photon. Nu C is the threshold frequency or cutoff frequency, or we can say it critical frequency. And what about the threshold frequency? We'll define it later. And don't ever forget, EW is the work function. If the third probability, if the photon energy is less than the work function, so we started assuming that it is equal to the work function. Electron is freed, having no kinetic energy. If it is above, having a higher energy, the difference appears as kinetic energy. If it has an energy less than the work function, the electron will not be freed. No matter how intense the light is, no matter how many photons fall on the electron. This is the most important piece of information. I'll say it and please bear it into your mind. The electron cannot absorb more than one photon. So the energy per photon should be sufficient to extract it. It has nothing to do with the intensity. Intensity means the number of photons, but it has to do with the frequency of the photon. Frequency of the photon is the energy of the photon. Energy per photon should be above a certain value. We call it work function, so as to extract electrons from the surface. Intensity has nothing to do with the phenomenon. Yes, it affects when each photon has enough energy. Okay? When each photon has enough energy, when you use many photons, we'll be able to eject more electrons. Okay? Bear this into your mind. So if the photon energy is less than the work function, the electron will not be freed at all, no matter how intense the light is. We've got facts about photoelectric effect. First, for any metal, electrons are only emitted if that is the important thing, if the frequency of the incident light is above some threshold value. We call it critical frequency, µc. So weak ultraviolet has very short wavelength, high frequency. So energy per photon depends on frequency. Energy that each photon, ultraviolet photon, possess is very high, so it is capable of extracting electrons. So weak ultraviolet can emit electrons from zinc, whereas very intense infrared cannot. Pay attention to this piece of information. Infrared photon means photon has, yes, long wavelength. Short has long wavelength, low frequency. So energy per photon is, yes, is small. It is less than the work function. Yes, so we cannot use infrared to extract electrons from zinc, no matter how intense the radiation used, how intense the infrared radiation used. Okay, it depends on energy per photon, and energy per photon depends on frequency. Okay, if one photon had the ability to extract electron, then many photons, yes, can be used to extract more and more electrons. Okay, even though it is delivering far more energy per second, this is the intensity to each unit area of the zinc. Okay. What about the threshold frequency? It depends on the metal. And the maximum kinetic energy of the ejected electrons depends on the frequency of, this is a very important piece of information. The maximum kinetic energy of the ejected electrons, velocity of the electrons ejected from the metal, depends on frequency. Okay, if frequency of the incident ray is equal to the cutoff frequency, kinetic energy will be equal to 0. As the difference increases, okay, in favor of the incident radiation, kinetic energy will be increased. If it is less, it won't be able to eject electrons. So it is proportional to the difference between the incident light frequency and the threshold frequency. I'm talking about the maximum kinetic energy of the ejected electrons. The threshold or cutoff frequency or critical frequency can be defined as, it is the lowest frequency of an electromagnetic radiation needed to eject electrons from the surface of a certain metal. Let me say it again. It is the lowest frequency of an electromagnetic radiation needed to eject electrons from the surface of a certain metal. Okay, we've got some questions. What is the photoelectric effect? We've got questions. Let's try to answer them together. It is ejection of electrons of some metals by light of certain frequency. The most important words here, certain frequency. Frequency is the deciding factor. Yes, frequency, as a matter of fact, determines the energy of the photon. And energy of a single photon should be greater than a certain value. We call it work function. Okay, so the most important factor, the crucial factor of the phenomena is frequency. Okay, we've got another question. It says, why does blue light eject electrons from certain photosensitive surface from a metal, whereas red light has no effect? We used blue and red. Blue light managed to extract electrons, but red could not. Even if we use red light, very intense red light. Okay, what is the difference between red and blue? Red has it has the longest visible wavelength, but blue has the shortest. Short wavelength means high frequency. High frequency means high energy. So the energy per photon for blue light is much greater than the energy per photon for red light. Okay, so the answer is blue light has higher frequency. That is to say, it has more energy per photon than that of red. Okay, we've got another question. Will bright blue light, bright blue, bright means, yes, we've used blue light, we've used many photons of blue light. It has high intensity. Bright blue light. Will bright blue light eject more electrons from a certain photosensitive surface than dim light of the same frequency? Yes, we'll see the answer. Okay, yes, of course, because bright blue light has more photons, and since each photon is capable of ejecting electrons, we expect to have more electrons ejected. Yes, because bright blue light has more photons than dim blue light. Another question, in the photoelectric effect, does brightness or frequency, this is very nice question, brightness or frequency determine the kinetic energy of the ejected electrons? Of course, I expect all of you to know the answer. It is frequency, of course. It depends on frequency. Okay, frequency determines the kinetic energy, whereas brightness determines the number of electrons ejected when each photon is capable of ejecting electrons. Okay. Another question, does the photoelectric effect support, this is very important, the particle model, modern physics, or the classical model, wave model of light? Of course, it supports the particle model. It supports the particle model. It is, yes, we still use the term quantization of energy. So it supports the particle model. In a photoelectric emission experiment, okay, this is very important question. A metal surface in an evacuated tube was illuminated with monochromatic light. Photoelectric emission experiment, a metal was illuminated with monochromatic light of frequency greater than the threshold frequency. What does this mean? It means each photon is capable of ejecting electrons. Since the frequency is higher than the lowest required one, the threshold frequency. Since it is higher than the critical frequency, it can, yes, extract electrons. Okay. If the experiment is repeated, if the experiment is repeated with light of the same wavelength, same frequency, but twice the intensity. Twice the intensity, we used, yes, much more number of photons. Twice the number of photons, okay? What effect will this have on the photon energy, the maximum kinetic energy of the photoelectron, the electron ejected, okay? We'll take it one by one. And finally, the work function of the metal and the photoelectric current intensity. So we want the effect on 4 things. Let's take it one by one. Photon energy depends only on frequency, so it won't be changed. It remains unchanged. So the photon energy will not change. Okay. Concerning the first item of the question. Maximum kinetic energy depends only on frequency. We didn't change the kind of light we used, so it remains unchanged. Maximum kinetic energy of photoelectrons will not change. Why? It depends on frequency. We used the same color. Okay, what about the work function? It depends on the metal, and we illuminated the same metal, so it won't be changed. And finally, photocurrent, yes, number of electrons ejected will be increased by increasing the intensity of the incident radiation. Okay, another question. A metal surface is illuminated with the monochromatic radiation whose frequency is greater than threshold frequency. Okay. Explain how to increase the number of photoelectrons emitted per second, how to increase the maximum kinetic energy of the photoelectrons. Okay, this is the core of the lesson. To increase the number of electrons ejected, we can increase the intensity. Yep. So, by increasing the intensity of the incident radiation, we'll increase the intensity of the photoelectric current. Okay, and how to increase kinetic energy of the ejected electrons? By using another radiation of higher frequency. The incident light is replaced by another light having higher frequency. Okay, the incident light is replaced by another light having higher frequency. Okay, we've got an interesting question. The following table illustrates the response of some metals when exposed to different frequencies of electromagnetic radiations. Okay, let's look at the table. Metal, okay, zinc, we used ultraviolet and it managed to extract electrons from it. Blue, no. Red, of course not. Red is, yes, incapable of ejecting electrons. And another metal, sodium, ultraviolet, managed. Blue, yes, managed this time, but red, no. And finally, cesium. In cesium, all radiations are capable of ejecting electrons from the surface of cesium. Okay, ultraviolet managed to eject, even red managed. Okay, look at this table. So it is so easy to eject electrons from cesium, but the most difficult one is zinc. Okay, what about the question? Which metal has the greatest work function. It means which one of them is the hardest to eject electrons from it. Of course, it is zinc. Okay. Which one of them had the highest threshold frequency? It is the same. It is the hardest to eject electrons from, to extract electrons from. It is zinc. Another, which one has the longest threshold wavelength, means lowest critical frequency? Okay, it is cesium. Thank you very much. And finally, which one of them has the least work function? I guess all of you know it. It is the easiest one to extract electrons from. It is cesium. In this way, we've come to the end of this edition. Until we meet again, my best wishes to you all. Stay blessed and safe. Goodbye.